Complex equations. A complex equation is an equation whose solutions are complex numbers. Like real equations, there are many different types of complex equation. Type 1, linear equations. A linear equation in Z is an equation of the form AZ equals B, or an equation that can be rearranged into this form. As with real numbers, we can solve this equation by dividing across by A. So dividing both sides by A, we'd end up with Z equals B over A. However, if A is a non-real complex number, then we have to multiply above and below by its conjugate to calculate Z. Example, solve the equation 3Z over Z minus 2I equals 1 plus 2I, where I squared is equal to minus 1, for Z, which are elements of the complex number set, and express your answer in the form of A plus BI. This equation can be rearranged into linear form. So we have 3Z over Z minus 2I equals 1 plus 2I. So we multiply both sides by Z minus 2I. So we get 3Z equals 1 plus 2I multiplied by Z minus 2I. Multiplying out our brackets, we get Z plus 2IZ minus 2I minus 4I squared. We bring everything containing a Z to the left-hand side and anything without a Z to the right. So we have 3Z minus Z minus 2IZ is equal to minus 2I plus 4. We simplify. 3Z minus Z is 2Z, and everything else stays the same. We divide across by 2, so we get Z minus IZ equals 2 minus I. We factorize our two terms containing Z, so we have Z times 1 minus I equals 2 minus I. And then to get the Z on its own, we divide across by 1 minus I. So we get Z equals 2 minus I divided by 1 minus I. Next, we're going to multiply the top and the bottom by the conjugate of the denominator. So the denominator is 1 minus I, so we're going to multiply the numerator and the denominator by 2 plus I. So we end up with 2 minus I multiplied by 1 plus I, which gives us 2 plus 2I minus I squared, and 1 minus I multiplied by 1 plus I. The quick way to do this without doing it out the long way is to square the real part, so 1 squared will give us 1, and then square the imaginary part, so minus 1 squared will also give us 1, and 1 plus 1 is 2. And simplifying the numerator, the minus I squared will become minus 1, which will be plus 1. So we have 2 plus I plus 1 over 2, which gives us 3 plus I over 2, which gives us 3 over 2 for the real part and 1 over 2 for the imaginary part. So our complex number is Z is 3 over 2, or 3 halves, plus a half I. And now it is expressed in the form of A plus BI. Type 2 quadratic equations. A complex quadratic equation is an equation in the form of AZ squared plus BZ plus C is equal to 0, where A, B and C and Z are elements of the complex number set. These equations have many features in common with real quadratic equations from algebra, but there are some differences. The solutions, or roots, can be found using a familiar quadratic formula. So Z equals minus B plus minus the square root of B squared minus 4AC divided by 2A. So we're used to seeing this as X equals, but when we're dealing with complex numbers we have Z equals. So we can use this even if some of the coefficients are not real. Solve the equation Z squared minus 4Z plus 13 is equal to 0. For Z, elements of the complex number set. We will use the quadratic formula from our formula book, also known as the minus B formula to some people, with A equal to 1, because we have an invisible 1 stuck onto the Z squared, B equal to minus 4, because there's a minus 4 stuck onto the Z, and C equal to 13, because the constant is 13. Subbing into our formula with A, B and C, we end up with z equals minus minus 4 plus minus the square root of minus 4 squared minus 4 times 1 times 13 divided by 2 times 1. Simplifying, we get z equals to 4 plus minus the square root of minus 36 all over 2. Now the square root of minus 36 can be broken down as the square root of 36 multiplied by the square root of minus 1. And the square root of 36 is 6, and the square root of minus 1 is I. We have to learn this off by heart. The square root of minus 1 is equal to I. So the square root of minus 36 is actually 6i. So that's where the 6i comes from. And 4 divided by 2 is 2 for the real part. And 6i divided by 2 is 3i for the imaginary part. So our complex number z is equal to 2 plus minus 3i. So our two solutions for this equation are 2 plus 3i and 2 minus 3i. If we had been asked to solve the equation for z as an element of the real number set, then there would have been no solution. Part 1. Find the real numbers p and q if p plus qi squared is equal to minus 3 plus 4i. And part 2. Solve the equation z squared minus 3 plus 4i z minus 1 plus 5i is equal to 0 for z elements of the complex number set. So part 1, we want to find the real numbers p and q. So we have p plus qi squared equals minus 3 plus 4i. Multiplying out the brackets, we get p squared plus 2pqi minus q squared, and that's still equal to minus 3 plus 4i. And then we're going to put the real parts together and the imaginary parts together. So p squared minus q squared goes into brackets because that's the real part. And 2pqi is the imaginary part on the left of the equal sign. And on the right we still have minus 3 plus 4i. So you put the real equal to the real. So p squared minus q squared is equal to minus 3. So that's the real part, and that's equation 1. We'll use that again. And now the imaginary parts equal to the imaginary parts. So 2pqi, we just forget about the I, equal to 4i. Again, we forget about the I. And now what we're going to do is solve for q. So we're going to have 4 divided by 2p will give us 2 over p. So q is equal to 2 over p, and this is equation 2. And again, we're going to use that again. So we're going to take the first equation, which is the more complex one because it had squareds in it. And we're going to substitute into it the q. So we had q equals 2 over p. So we swap that q for 2 over p. But remember, it's squared. So we're going to square the numerator. So 2 squared is 4. And square the denominator. So p squared is p squared. So we get p squared minus 4 over p squared is equal to minus 3. So to break up this fraction, we're going to multiply across by the denominator. So we're going to multiply each term by p squared. So p squared by p squared is p to the power 4. Then we just have minus 4 because we can cancel out the denominator. And minus 3 by p squared is minus 3p squared. Next we bring everything over the left hand side. So the minus 3p squared comes over the equal sign and becomes positive 3p squared. So we have p to the power 4 plus 3p squared minus 4 is equal to 0. Next we're going to factorize. So since this is p to the power 4, we've got p squared in the front of this bracket and p squared in the front of that bracket. The factors of minus 4 are going to be 2 times 2 and 1 times 4. So we're going to have minus 1 times positive 4, because minus 1 plus 4 is 3. Next we're going to let the first bracket equal to 0. So p squared minus 1 equals 0. So p squared is equal to 1. So p is equal to the square root of 1, which is plus or minus 1. And then again we have the other bracket, p squared plus 4 is equal to 0. So p squared is equal to minus 4. And at this point we would say then p is equal to the square root of minus 4. But this is not possible as p is a real number. And we know that from the question. Find the real numbers p and q. So our p values are going to be plus and minus 1. Now we need to find our q values. So we take one of the equations, preferably the simpler one. So we're going to take q equals 2 over p. We're going to sub in p value of 1. So 2 divided by 1 is going to be 2. So p plus qi is going to be 1 plus 2i. Then we take the second p value minus 1. So we get 2 divided by minus 1, which is minus 2. So p plus qi is minus 1 minus 2i. Thus, the square root of minus 3 plus 4i is equal to plus minus 1 plus 2i. Part 2. Solve the equation z squared minus 3 plus 4iz minus 1 plus 5i is equal to 0 for z elements of the complex number set. So we have a quadratic equation because we have a z squared, a z, and a constant. So to solve a quadratic, we're going to use the minus b formula, or the quadratic formula from our formula book, which is minus b plus minus the square root of b squared minus 4ac divided by 2a. So for the equation, a is equal to 1, because z squared is technically 1z squared. B is equal to minus 3 plus 4i, because minus 3 plus 4i is stuck onto the z. And c is equal to minus 1 plus 5i. So minus 1 plus 5i is the constant at the end. So, substituting into our formula, we end up with minus 3 plus 4i plus minus the square root of minus 3 plus 4i squared minus 4 times 1 times minus 1 plus 5i, all divided by 2 times 1. Then we simplify. Minus times a minus gives a plus. Minus 3 plus 4i squared will give us 9 plus 24i minus 16. So be careful here because you have to look very closely. The squared is outside the square brackets, and what's inside the square brackets is minus 3 plus 4i. So we have to multiply in the minus first, so we end up with minus 3 minus 4i to be squared. So minus 3 minus 4i squared gives us 9 plus 24i minus 16. And then minus 4 times 1 is minus 4. And minus 4 by minus 1 is plus 4. And minus 4 by plus 5i is minus 20i. Next we're going to simplify underneath the root. So 9 minus 16 plus 4 is minus 3. And 24i minus 20i is plus 4i. So the square root of minus 3 plus 4i, we worked out in part 1 to be plus minus 1 plus 2i. So we swap this for this. So next we're going to break up our question into two parts. So we have a plus minus here. So we're going to have a plus here and a minus there. And then we just simplify. So 3 plus 1 is 4, adding the real parts, and 4i plus 2i is 6i, adding the imaginary parts, and that's all over 2. And then 4 divided by 2 is 2, and 6i divided by 2 is 3i. So 2 plus 3i is our first answer. Now we work on our minus. So 3 minus 1 is 2, and 4i minus 2i is 2i. 2 divided by 2 is 1. And 2i divided by 2 is I, or 1i. So 1 plus I is our second answer. So we were asked to solve the equation. So our two answers are z equals 2 plus 3i, or z equals 1 plus I. 3. Equations containing conjugate or modulus. If an equation contains the conjugate of z, z bar, or the modulus of z, then the preferred approach is to let z equal x plus yi. After simplifying both sides of the equation, we can use the definition of equality to write down and solve two simultaneous equations in x and y. Example 4. Solve for z elements of the complex number set the equation 2z plus 1 plus I conjugate z equals 5 plus 3i, where z bar is the complex conjugate of z. So our solution is, let z be equal to x plus yi, then the conjugate of z is x minus yi. So we're going to write out our equation, 2z plus 1 plus I conjugate of z equals 5 plus 3i. We're going to swap the z for x plus yi and swap the conjugate of z for x minus yi. Next we're going to multiply out the brackets. 2 times x is 2x, 2 times yi is 2yi. And then multiplying out the brackets here, 1 plus I multiplied by x minus yi will give us x minus yi plus xi plus y. And that's all equal to 5 plus 3i. Next we're going to put the real parts together and the imaginary parts together. So the real parts, basically anything without an I, is 2x plus x plus y with brackets around it, plus, and then the imaginary parts, 2yi minus yi plus xi, and that again is equal to 5 plus 3i. Next we simplify. 2x plus x is 3x, and we still have plus y, so this is the real part. And then 2yi minus 1yi is technically 1yi. So we have yi plus xi, so we can factorize the I outside the bracket. So we have x plus y. And this is the imaginary part. And next we're going to let the real parts equal the real parts. So 3x plus y will be equal to 5. And the imaginary parts equal the imaginary parts. So xy will be equal to 3 because we'll drop the i's. So real parts equaling real parts. 3x plus y is equal to 5. This is equation 1. And imaginary parts equaling imaginary parts. So x plus y is equal to 3. This is equation 2. Next we're going to solve simultaneously. So we just write out equation 1 again. 3x plus y is equal to 5. And equation 2 we're going to multiply by minus 1. So we get minus x minus y equals minus 3. Our y's can now cancel. So we have 3x minus 1x is 2x. 5 minus 3 is 2. So solving for x, x is equal to 1. And solving for y, y is equal to 2. Thus, z is equal to x plus yi, which is 1 plus 2i.